Welcome back. This is lecture 27. Till now we have covered a lot of ground, but we have assumed certain things, right? So we have assumed so far that all the while we did our noise analysis, while we did our matching analysis, while we are doing our distortion analysis, we continuously assume that we have access to very good inductors, ideal capacitors at our disposal, right? But as it turns out, that's actually not the case, especially when you are doing integrated circuits. Now here I would like to make a distinction between discrete level or board level or a printed circuit board level integration of RF modules versus doing a complete full chip RF module. And while there are a lot of advantages of integrating everything on a chip, one of the major disadvantages is the passives that you get, that is the inductors and the capacitors, which are so essential for filtering purposes for RFIC applications. They are not as good. In fact, they are quite bad with respect to their off-chip counterparts, right? You get very good. When I say very good, what I mean essentially is that an inductor behaves like a close to an ideal inductor if it's an off-chip inductor. A capacitor behaves almost like an ideal capacitor if it's an off-chip capacitor. Obviously, they have certain limitations at higher frequencies. You'll probably not be able to transfer signals from outside the chip to the inside the chip. Those, having said that, even those, I mean, with as much efficiency as you would like to do, but having said that, an on-chip passives have certain challenges which are unique to integrated circuit passives, right? So these challenges often are not, one doesn't have to encounter if you are integrating discrete level components, right? So what I would like to do in today's lecture is to walk you through some of the issues that one might face and how to go about at least estimating them, right? And what are the some of the design considerations that you might want to have while making while implementing these passives, right? So let's start off with inductors, right? Now, if you recall, in one of the earlier lectures, I had talked about the typical realizable values of inductors on a chip. So as it turns out, how do you essentially make an inductor, right? So from our high school physics understanding, we understand that the inductors are essentially pieces of wires which are wound together in certain ways, and the magnetic fields align, and there is a flux that goes through each of these turns, and they couple. Higher the number of turns, more their coupling, more the amount of flux, and the rate of change, and essentially this is proportional to I, and the rate of change of flux gives rise to some impedance, and those proportionally constants give rise to effective inductance, right? So now, if I have to realize an inductor, I'll have to make these loops, and as it turns out, if you again recall the basic our basic high school physics, the value of an inductance is directly proportional to the area, because ultimately I have to, in order to get I have to ensure that a lot of flux cuts the loop, right? So if I have to increase the value of the inductance, I have to ensure that a lot of flux, I mean, more the area of the loop, better it is, and hence it becomes area intensive. Now the problem that is unique to IC design is that if you recall the metal stack that I had talked about in one of the earlier lectures. So if this is your substrate, your metal stack is something like this. You have one metal stack here, so I call this M1, and by the way, this is oxide here. In between you have oxide, then you have M2, and so on, right? Depending upon which technology you have, you can have 3, 4, 5, 6, 7, 8, 9 metal layers, one on top of the other, right? So now, let's assume you would want to make an inductor. How do you go about making an inductor? So after that, in a certain way, you can think that from it, your IC design is essentially a planar topology. Even though you have multiple layers of metals, if you have to go from one metal to another, you'll have to connect them via vias, which are essentially tunnels from one level to another. And as it turns out, these vias are not very efficient in terms of their in terms of the unit resistance that they provide. So the most effective way of designing an inductor is essentially then to draw circles on a planar topology, right? So let's say I have a top level view. So by the way, this is a cross sectional view. This is cross section. So if I do a top level view, so let's say I am doing a top level view, right? And top level view, let's say this is M4. Just for the sake of argument, I am calling this M4. So how do you go about designing loops here? You might say that I want to make a loop, something like this, and maybe I take the current out and so on. Maybe the current goes this way, comes out this way, and this forms my loop, right? But then only one loop of where probably will not give you sufficient amount of inductance, right? When I say sufficient, again, when I am saying sufficient, I am essentially trying to get into the territory that is useful for designing these LNAs and all, right? So I'm talking about maybe few nanohenry, maybe 10 or 20 nanohenry kind of inductance. That is the target inductance that we are talking about. And as it turns out, even to get to 10 nanohenry of inductance, you will end up taking a significant amount of chip area. Almost, I mean, it's not surprising to see chip areas of almost 1 millimeter square taken up by inductances of these values, while the total chip area of an RFIC can be like few tens of millimeters squared, right? So as you can see that only making one inductor can become very area intensive. Now you might say that, hey, what's the problem? Why are you saying that I can do only planar? Because if I have so many metal layers, maybe I can have one of these, maybe I can have one of these loops here, I can have another loop here, I can have another loop here, and then connect them via via, right? But the issue there is, as it turns out, in most RF process, there are a couple of issues. As it turns out, first issue is in order to make sure that the flux lines are tightly coupled, you have to ensure that these metal layers are as close to each other as possible, right? And as it turns out, this thickness is not in your control. This will be given to you by fab. That might be enough, that might not be enough, but the key thing is that is not in your control, right? And number two, the next problem is, the more important problem is, as it turns out, these metal layers, all of them do not have the same type of resistivity. Generally, the other thing that you'll have to take care is, moment you get hold of a technology in which you are planning to design an RF system, you have to characterize the resistivities of each of these metal layers. Generally, in a process design kit that you are going to use, the top level, if it is a RF friendly process, the top level metal will have the least resistivity, and the lower level metals generally have higher resistivity. Again, this is not sacrosanct, but this if you get hold of an RF process, this is what generally one might see, right? So given that you have difference in resistivities, and the top metal layer has the least resistivity, then which one would you like to use? Ultimately, you want an inductor whose resistance is 0, right? Which means that you would like to use the top metal layer only. So which essentially means that you ended up with for all practical purposes, you have only one sheet in which you can draw circles, right? So which essentially means that you are limited by the topology that you can use in a CMOS process. Let's say this is your top layer. Again, this is the top view, and this is the top view, let's say. And how would you like to go about making your inductor? Maybe I'll use a thicker pen. So maybe you can go about using inductors like this and so on, right? And obviously if the current has to go in, right, if the current has to go in, it also has to come out. So while coming out, maybe you can have you can jump to a lower metal layer through a via and then come up and take it out, right? So this can be a lower metal layer. It's a top metal layer. Okay. Now the story does not end there, because now in an ideal inductor, what do we want? So how do you know whether one inductor is good or bad? So a good inductor, so characteristics of a good inductor. What are the characteristics of a good inductor? Firstly, obviously we need to have, I mean, the basic thing is that you should be able to make any value of inductance that you want, right? So different values, or that is a good inductors, good inductor topologies. Different realizable values of L, right? Number two, second thing is that once you know that I can realize different values of L, the other thing is that you have to ensure that they do not have any series resistance, which is not possible because you have metal lines, and metal lines are real, they are not ideal, which means they are going to be associated with some resistivity, right? But the job is to ensure that the resistivity is as low as possible. So resistance, so you should have low resistance, right? And third is you should have, this is not very obvious if we do not think about it, but third is that if there are any associated capacitances, right, you would like to minimize them as well, because ultimately you are trying to make an inductor, not a capacitor, right? Low parasitic capacitances, correct? Okay, so at a very top level we understand this, right? So this is what we need. Now the thing is, we'll try to understand whether, let's say, if we make these kind of spiral inductors, because spirals, this kind of spiral inductor, then what are the issues that one might face? Firstly, let's take the resistance. Let's attack the resistance piece. So let's take one simple metal line. So let's say I have a simple metal line. Now I am not taking the top level. I am showing you kind of a three-dimensional, trying to show you a three-dimensional view, right? So your current goes in, current comes out. So naturally, every piece of metal has a resistivity associated with it. And generally, if you look at in many RF processes, the top metal layer is copper, and there is certain amount of resistivity associated with it. It's typically of the order of 50 milliohms per square. Now, what is the definition mean? The definition essentially means that, so if you look at if you look at a piece of metal, what are the dimensions that are that is in our control? When I say hour, I mean as circuit designer's control. So note that the metal has three things. It has the width, it has the length, I should say small l, because capital L I am using for inductance, and here is the height. And as it turns out, this height is not in the control. It's not a designer variable for a circuit designer. It is a designer variable for a device designer or a process designer. So once you get your process design kit, you will not be able to change h, right? So this is true for all integrated circuits. The vertical dimensions are never in our control. The only things that are in our control are L and W, right? So now if I have to let's say for a given topology or a given piece of wire, I have to increase or I have to decrease the resistance. What should I do? I have to increase the W, right, or reduce the L, right? So essentially that W and L, just like MOSFET, the W times L essentially, or the individually W and L are responsible for setting the resistance, right? Now let's say I have a piece of wire. Now I am showing you the top level. Now if I have a piece of wire which has this much of W and this much of L, and I have another piece of wire which has half W and half L. This is W by 2 and this is L by 2. Which one do you think will have higher resistance between these 2 points, between A and B, between C and D? So what can you, and if I neglect all the other second order effects, what can you comment on the resistance between RAB and resistance between RCD? Clearly you see that if I understand our very basic formula, that resistance is the resistivity times the length divided by A. A is a cross section, right? So which is W times H, where H is fixed in both the cases, both the topologies, because it is not a circuit designer's control. So essentially that L by W is something that is of importance, right? So essentially in this case you see that the effective L by W is same in AB and CD, so RAB is equal to RCD, right? So ultimately then what are you interested in? I am interested in for a given W, right, what is the L, right? For a given W where L is large, then I have a large resistance. If for a given W if L is small, I have a small resistance. In other words, I am interested in is how many squares I can build as I traverse the length of the wire, right? So here you can see that this is one square, this is another square, and this is another square. So I can build 3 squares, right? So in case of the structure on the right, how many squares can I build? Here also I can build 3 squares. Because I am able to build same number of squares while traversing the length of the go from A to B while encompassing the entire W, obviously, then that is why I can say that I have same amount of resistivity. So hence in IC design, the measure of resistance or how good a metal that we have is basically the resistance per square, right? So and hence it's called the sheet resistance, right? So measure of resistance in ICs is called sheet resistance or resistance R per square, right? And its unit is typically, it's basically resistance per square, where square is unitless, because I know that a square of this size and a square of this size will have the same resistance from either way, right? So it's basically resistance per square. The unit is ohm per square. So now that we know how to characterize a resistance of a wire, so what options do we have to decrease the resistance? all we have to do is to reduce the number of squares. And how do I reduce the number of squares? I have to make the thing to make the wire wider and wider, right? I mean, that's already we knew, but this is one way of formalizing it. But the issue is, whatever this formula of rho L by A that we have, firstly, this is only true for a perfectly rectangular geometry and without having any, while we assume that the current only flows through the rectangular slab and there is no fringe electric field and so on and so forth, right? But the issue is, at higher and higher frequencies, right, something strange starts to happen. So as you increase frequency in a piece, as it turns out, as we increase frequency, the electric fields tend to get localized only at the surface of the wire, and don't really move inside the. They are not essentially equally spread around inside the conductor. So right. So what ends up happening is most of the current actually flows around the surface of the inductor, right? So as you increase it, I mean, I'm sure you have heard of this in your undergrad electromagnetic classes also. This effect is often called skin effect, and the depth at which the electric field drops to 1 by E, right, of its surface is called the skin depth, right? So generally, because of skin effect, the electrons or the electrons or the carriers, you can think of, they are localized around the surface boundary of the conductor, right? So because of the skin effect, so the skin depth is, as it turns out, is in proportional to 1 by under root f. What is this telling us? This is essentially telling us that as the frequency increases, your skin depth reduces, which means the electric field is mostly localized around the surface of the conductor, which essentially means that all the carriers that are contributing to signal flow will be localized at the around the surface of the conductor, and which essentially translates to the fact that your overall resistance will increase, because now, even though you have this big fat wire, the entire wire is not being used for the purpose of conducting current, right? Only the thin or thick doesn't that is relative, but only a layer of conductors or electrons are contributing to most of the signal flow, right? So which essentially means that it doesn't really matter that you keep increasing W, even though the static model of resistance, which essentially tells us that the total resistance can be reduced by reducing the number of squares, but at high frequencies, as you see, that the skin depth can start dominating, right? A typical number of skin depth is in copper at 1 gigahertz. The skin depth is approximately 2 micrometer. And just like this, I mean, skin depth definition is basically where electric field drops by 1 over E. And if you basically say that I will take 4E, let's say, I mean, it's equivalent to the time constant examples. If I want to take 4 time constants to encompass most of, if I have to take, just like in an RC circuit, you say that we want to take 4 time constants to ensure perfect settling or very good settling, or some 95% or 99% of the settling. If you want to draw the same analogy, then you basically say that I would like to have 8 micron distance from either side, right, at 1 gigahertz, right? So which means that if you have 16 microns of width of a copper wire, you are done, right? Even if you make like 100 micron or 20 micron, you will not gain much. The resistivity will not, the resistance will not really drop. But if you go at 4 gigahertz, the skin depth is essentially dropping to 1 micron, right? So the requirement of your copper, requirement of the thickness of your copper wire is now basically 8 micron, right? There's no point going to 20 micron wire because you are not going to use that 20 micron wire. Okay, that is something to take into account when you go to higher and higher frequencies, right? So this, so basically, what is the role of the skin depth? The skin depth is increasing your resistance, right? Okay, fine. So so till now, what are the two resistance contributor, loss contributor? One is the absolute value of the resistance, right? And second is skin depth, right? So there is a third contributor to resistance also, and that is as follows. Now note that when you are making a inductor, when you are making this spiral inductor, you can see you have current flow. Let's say you have a current flow in this direction, then again you have a current flow in this direction, and so on, right? So essentially, you see you have adjacent wires which are contributing to current in the same direction. That is good because ultimately it gives you the mutual inductance, right? If you have wires carrying currents in the same direction, you have mutual inductance, and that can give you higher and higher value of inductance, right? Which is good. But the issue is as follows. Now again, I am showing you a top level. So let's say you have this wire and you have this wire. Both of them are carrying current in the same direction, right? Now consider the current in wire A, right? So let's say this is the wire A and this is wire B. Now consider the current in wire A. So what will be the electric field in the, or rather what will be the magnetic field associated with the direction that I have shown? The magnetic field will be something like this, right? It will cut and go something like this. Correct? So it will go through the wire. Note that magnetic field can penetrate metals. So your magnetic field will you'll have a magnetic field which goes something like this, right? So now see what is happening to metal B due to the magnetic field on metal A, the part that is cutting the metal B, right? So now if you recall Lenz's law, what does it say? It basically says that whenever you have a magnetic field that changes, right, and you have a current carrying conductor, it is going to, or rather you have a conductor, it is there will be induced there will be induced current in that second conductor, so that it opposes the magnetic field that opposes the flux that the loop is cutting, right? So now consider there is a loop. I mean, where is the loop? It's a metal, you can have any loop of current, right? So consider you have this loop of current, you have a loop, okay? So what will happen in this loop? The direction of the current flow in the loop will be such that it is going to create a magnetic field in the opposite direction, right? And what will be that direction of current? And what will be the direction of the current? The direction of the current in this loop will be like this, right? Correct? So now note that the direction of the current around this edge, in the loop that has been induced is in the opposite direction of the current that the wire is trying to carry, which means that there will be some cancellation of current effective cancellation of current that will start happening around the edge of the wire, right? So now you see the problem. So now it essentially means that you are again effectively reducing the amount of space through which your effective current can move, right? Which essentially means that you will end up having higher resistance as well. Now one way to reduce the resistance is to not have these two spaces so close to each other, right? So increase spacing. But I mean, as you can readily figure out, if you keep increasing the spacing, you are going to have a problem with getting enough inductance, right? So how do you go about resorting it? There are many numerical models which can give you a approximate idea, but they are extremely process dependent and they're topology dependent. So the most practical way of going about doing this is running electromagnetic simulations, right? There are many freely available tools and some tools which are commercially used as well, which can be used to run these EM simulations, and it will give you the essential the resistances associated with the overall resistances associated with all which are associated with all the losses, right? So as you can see, I mean, all these effects, what are they doing? I mean, effectively I can bunch them together and say that there is a increase in resistance, right? So by the way, before I move on, this type of thing is called a proximity effect, right? So you are going to have increase in resistance due to skin depth, due to proximity effect. We are not done yet. So now, so by the way, how do I model these resistances so far? So I have these inductances. I can model these resistances as some series resistance associated with the inductance. Note that this should be a distributed resistance, but for the purpose of the modeling, I can say that this is the series resistance associated with the inductance. Okay. Next is what? Let's say this is a substrate, and this is where I am drawing this is where my inductor resides, right? So let's say that I have an inductor here. Okay. So now as it turns out, this substrate is also it's not a perfect insulator, right? It has conductors associated with it. It has basically mobile holes associated with it, and the top metal layer is not like at outer space, right? It is sitting on the same chip, which means it has a close proximity to the substrate, which essentially means that I can model I can expect some capacitances associated, distributed capacitance associated with the entire metal line that is on the top and the substrate. And to top it off, I know that there is a substrate is p-type, right? Which means that there is ultimately the substrate is grounded, right? So how is the substrate grounded? The substrate will probably have a contact here, and you'll have some sort of vias which will go all the way up through multiple metal layers, and it will effectively be grounded. So which essentially means that you have resistances associated with this, well, and it goes to ground, right? So what's the problem that you are seeing? So not only you have this model, you have models of, you have a resistance, capacitance, resistance, effectively to ground, correct? So now this resistance now what is the source of this resistance? This resistance is essentially the resistivity of the p-type material. So how do I, if I want to reduce that loss, what can I do? I can say that instead of putting a p-type material there, I can put a metal 1 sheet underneath, right? So I can put a metal 1 sheet underneath, say. So what I mean is, let's say I have this, I say that underneath, let's say I make say another metal, let's say I call this metal 1, and let's say this was metal 4. I make a metal 1 sheet underneath and then ground it, right? So does that mean that my equivalent resistance model becomes this? and there is no loss. It would seem like that, but the issue is far more grave. The issue is, now you see that you have a loop on top and you have a continuous metal in the bottom, right? And because of that, the magnetic field that is going to cut, the flux that you are seeing that is going to cut here is going to create eddy current, is going to create just like the proximity effect, you are going to have a eddy current here, and the eddy current direction will be such that it opposes the electric field, the magnetic field, which means that if the current here is in this direction, the current within M1 will be in the opposite direction, so that the current magnetic flux cancels, and which means that you are going to have a reduction of effective inductance, right? The effective inductance itself will go down, right? Forget about the loss. Okay, so you cannot really do this directly. So what people figured out were smart ways of doing it, that if I want to reduce this loss, what I can do is, instead of giving a continuous strip of metal, I can break the metal into multiple. So basically you can now assume that this is this underneath. It's not a continuous strip of metal. So here what I'll do, I will break the metal into small strips. This is all underneath, right? It's all underneath. I'm breaking this metal into small strips. This is often called patterned ground shield. So what does it do? So if I break this and I connect all of these metals, and I connect them effectively to ground, right? So I get this effect, but without the effect of the loops cancelling, the eddy current loops cancelling the original inductance, because there is no continuous eddy current loop that can now flow, because the metals are not continuous, right? So pattern ground shield helps in reducing kind of the substrate loss without reducing effective inductance significantly, right? So that is something that is some trick that one can play, right? Okay, what else? So now effectively, what is our model? Now my inductor model, you see, is continuously evolving. So my resistances are, so now because inductor is a symmetric device kind of, so I would like to also have the model look symmetric. So this original R, I can break it up into two parts, and this capacitance here, this capacitance here, and even though I will have a reduced resistance, but the resistance will still be there, which is in series with this, right? So this will be there. Now because you have these ultimately these terminals of wires, right? Because you have to form a loop, so you have to, just like you saw it here, you have to bring the wire out, right? And you are going to form a loop, right? So because you are going to form a loop, and the wires have to be placed close to each other when they are coming out, right? So there will be a capacitance between those two terminals also, basically because of the physical proximity of the wire. And also, not only that, you have a distributed capacitance simply because these wires are also connected physically, they are also co-located physically close to each other, which essentially means that you will probably have a capacitance connecting these two terminals as well, right? So so once you have all of these things, right, so this probably is a much more realistic estimate of a model, but as you can see that this quickly becomes infeasible, right, to get any intuition. So I mean, once we have these models, which maybe your your EM simulator might throw out, I mean, it becomes difficult to make sense of what it is as a designer, right? We would like to have a simple way of, maybe a graphical way of understanding what's happening, right? So let me call this R sub, the substrate, right? So if I do a simplistic, if I model it as a slightly simpler model and say that what is happening at fairly low frequencies. So let's say this is the resistance that is in series with the inductance. So at very low frequencies, let's say this is, so if I plot, let's say, imaginary AB part of ZAB by real part of ZAB, what am I going to get? At very low frequencies, all right, the real part of ZAB is basically RS, and the imaginary part is omega L. So at very low frequencies, I am going to see the increase of this term, right? But note that at a slightly higher frequency, this RS, which at lower frequencies, this RS comprises of the physical resistance, right? Rho L by A kind of resistance. But at higher frequencies, right? So at higher frequency, this is low frequency. As frequency increases, so I am going to see this R in addition to RS, I am going to see R skin, which is also proportional to, which is a function of omega and increases by under root omega, right? So what am I going to see? So I'm going to see the increase in the real part of the impedance, and the imaginary part remains. I mean, it increases. The imaginary part is kind of increasing with as omega times L, and the R skin, due to the R skin, the real part will also start increasing, but at under root omega, right? So basically, the slope of this curve is going to reduce. So I'm going to see something like this, right? And even when you go to even higher frequencies, what's going to happen, right? So at very high frequencies, and now I'm going to make an approximation. So let's assume that I'm working at such a higher frequency, this C sub is shorted, right? If the C sub gets shorted, what am I going to see? I'm going to see this R sub to ground, right? So effectively at a very high frequencies, now you are going to see the current being, so this is at even higher frequencies, right? So you are going to see the current trying to bypass this entire, you might see that the current will try to bypass this entire thing and go to the ground via R sub, right? So you are going to see, because this is kind of coming in parallel, right? You are going to see the dominance of R sub, and this curve will eventually kind of taper down, right? And now note that now the question is, given that we plotted this kind of structure, what do you think? What is the optimum place for this for me to operate this structure at, given that I want to make it work like an inductor? So clearly, I would like to operate it somewhere here, right? So where it seems like the imaginary part of this reactance, right, is dominating, and on either side of it, on the left side of it, clearly, I have not maxed out the value of the inductance, right? The effect of the inductance, or on the right side of it looks like I have more and more loss, right? So in a way, in a way, I would like to ensure that in order to once we have this curve, right? So once you have this inductor model, so you have to basically characterize the inductor, this effective model, not only the inductance, to plot this imaginary versus by real versus omega, and then you see where is this maxima that you are operating, and operate the inductor around the maxima. Now, this is not in your control. That let's say I want to operate my inductor at 10 gig and my maxima is happening at 5 gig. That doesn't mean that I am going to change my operating frequency, right? So then what you need to do, you need to go and tweak the inductor design. And what are the controls? The controls are, you have to figure out what are the loss mechanisms that you are that are there, right? So obviously the skin effect is a loss mechanism that that you have to take care. Now, how do you take care of skin effect? One way to take care of skin effect is one way to take care of skin effect at very high frequencies is basically to say that I will not make my lines very thick, because they are kind of useless to make lines very thick. I would make it slightly thinner, so that my so that the effective inductance area goes down, and I am going to use multiple of these inductances, right? So if I use, so effectively I save area to some extent, but and given that having a larger area also causes large capacitances, large parasitic capacitance to ground. By making the area smaller, I can reduce that parasitic capacitance without too much of loss of without getting affected by the resistance as much, right? Because anyway at very high frequencies the currents are localized. There's no point in making very thick very thick wires, right? So that is one call that one might take. Another call that you might want to take, if you see that the proximity effect is probably causing a lot of issue, then you push out the spacings of the wires, right? But the key thing to note is that these are very technology dependent. So you have to first characterize the technology and see which type of losses dominate, and then move around the requisite frequency of operation, or move around the inductor topology in such a way that it matches your requisite frequency of operation, right? Okay, so let's stop here. In the next lecture we'll talk about capacitances and then move on, right? Okay, thank you.